All right, so I want to talk a little bit about this statement here, right? That sort of the crux of projectile motion, and that I've asked you to sort of accept until we start to study forces. But I want to sort of just chat a little bit about this concept and why it's true, and maybe hopefully show you a few videos and examples that'll help prove to you that it is in fact true. So we've made this statement that when you throw a projectile in the air, right, or push something off a table, shoot a gun, right, the projectile takes this sort of path, right? And I've told you that the horizontal motion of this object follows the constant velocity model. That is, it has zero acceleration, right? So its velocity is going to be constant in the horizontal direction. The vertical motion, however, follows a constant acceleration model where its acceleration is negative 9.8 meters per second squared. It's essentially in free fall if we were to isolate that vertical motion. And when you take these two components together, you get that sort of projectile arc that we've been studying. Why is this, right? Why does the horizontal motion follow constant velocity and yet the vertical motion follows constant acceleration? The answer is gravity, to be concise, right? The only force that is, we haven't really talked about forces yet, but we will get there. The only force on that object once it's thrown, kicked, whatever it's doing in the air is gravity. And gravity is a force in the vertical direction, right? It's not applying any horizontal force on this object. Therefore, right, there's only going to be a certain amount of acceleration in the vertical direction. This may not make too much sense to you right now, given the fact that we haven't talked about forces, but just as a sort of teaser for what we're doing next in the course, you may know this equation. It's one of the fancy ones that people throw out there. It's one of Newton's equation. F equals ma, right? This stands for force equals mass times acceleration. What this tells you is that there's a direct relationship between force and acceleration, right? Force and acceleration are directly related to each other. So if there's no force on an object, there can be no acceleration, right? And since there's no force on this object in the horizontal direction, it has no acceleration. In the vertical direction, however, there is a force on it, gravity, so it has some acceleration. Don't get too caught up in the weeds on this right now, but I know that some of you are unsatisfied with or dissatisfied with me just telling you that you need to accept this. So know that it has something to do with forces and Newton's equation. All right. So I want to show you a quick video here to hopefully help prove this to you, that in fact the motion in the horizontal direction is at a constant velocity, and in the vertical direction it is something of a free fall. So I could show this to you in class, but these gentlemen have created a lovely video that details it for us. The concept here is this guy has set up a experimental apparatus where on one end a ball will be simply dropped from this table. On the other end, a ball will be pushed off the table. And this will happen simultaneously through what he's rigged up. So the ball that's pushed is going to have some sort of component of velocity in the horizontal direction, and it's also going to be in free fall. The ball in the dropped condition will have no component of horizontal velocity, and it'll just be in free fall. What you should see is that the ball that's pushed will be traveling horizontally, but it will be falling with the same acceleration as the ball that's just dropped. In other words, its motion in the vertical direction will be the same as if it was never pushed in the horizontal direction. So let's give this one watch and see if you can catch on to what I'm talking about. So this ball here will be dropped, this one will be pushed. Let's see that one more time. And if I'm to pause it when the balls are falling, right, you'll notice they're at the same height. This one has traveled some distance away from its initial position in the x orientation, but they're falling at the same rate, right? Their motion in the y direction is identical, and they hit the ground at the same time. One more time, just for good measure. Right, you get the picture. There are plenty of sort of picture representations of this. This is one, right? This ball is dropped, this one is pushed, right? You can see that the balls have the same y component of motion, right? Their motion in the vertical direction is exactly the same, regardless of the fact whether or not they're moving in the horizontal direction. So what I would like you to do just to solidify this a little more and to practice some of the graphing skills that we worked on in class today is I want you to sketch a position time graph, a velocity time graph, and an acceleration time graph for both balls. So you're going to do in total 6 graphs, but you're only doing their motion in the vertical direction. Note, there's no need to use numbers here. I just want a general sketch, right? So I'm assuming that your signs are going to be correct, right? If something has a positive or negative position or velocity, that is correctly denoted, but it doesn't have to give an actual number. So you're going to do 3 graphs, a position time graph, a velocity time graph, and an acceleration time graph for the red ball's motion in the y direction, and you're going to do the same thing for the yellow ball's motion in the y direction, right? Note, important here, we're only graphing their motion in the vertical direction. We're not looking at their motion horizontally. If you have questions on that, you can email me, but I'm going to be looking for 6 graphs from you next class. One set of 3 that's for a ball that's dropped, and another set of 3 for a ball that's pushed off a surface, right? And those graphs are in the y direction. All right.